Here we are moving right along into section 5.3, which is one of the sections in calculus that you do not want to miss whatsoever. Obviously, some of the techniques that we saw in section 5.2 are not practical or efficient. Well, they might be practical, but they are not fully efficient. If we have a really long string of function values that we have to figure out and add up, times them by the delta x and such. So this section we are learning all about the powerful and practical way to evaluate definite integrals. So the first thing that we must look at is the area function. So we are going to let f be a continuous function for a value t that is greater than or equal to a. The area function for, I should just be singular, function for f with the endpoint a is a of x is equal to the integral from a to x of f of t dt. Okay, so we're making a definition here for that area where x is greater than or equal to a. Now, the area function here gives the net area of the region bounded by the graph of f and the t-axis on the interval from a to x, okay? So we have some variable changes here. Don't worry about it. Remember, these are just kind of some dummy variables. Here, this is telling me that I'm going from a to some value of x that I'm trying to find the area of. Call it 5 or whatever the case may be. So from 0 to 5 or something like that of a certain function, we're going to take the integral of that, okay? Hence gives us the area under the curve. Now, notice that it does say net area, so that can account for regions that are negative, that are positive, and that are negative. So make sure that you remember that and you take that into account. All right, so given this graph that I was just pointing at, the graph of f is given with the areas of various regions marked. So this area is negative 27, that area is 3, and this one is negative 35 because it's below. We are out to find, according to these two functions, we are going to find some area of these curves. So I'm going to start with a of 3. And I always go by taking, remember, this is an x value, so I'm going to go ahead and plug that right in there to that x. So that means I need to look from negative 1 to 3 of f of t dt. Now, this is f of t, and this is the t-axis instead of the x-axis. So again, they're just variables. They can change up whenever you least expect it. All right, so from negative 1 to 3, I want the area under the curve from x equaling negative 1 to x equaling 3. Here's negative 1, here's 3. So we're looking at the area that's down here in red. Now notice the area is 27, but since it's below the axis, we say that this is equal to negative 27. It's also asking me for f of 3, and f is just another area function where I'm starting not at negative 1 this time, but at 3 to x. So I want to do the integral. I'm going to put x equaling 3 up here, so I get from 3 to 3 of f of t dt. Now I wanted to do this one because I wanted to remind you of that. From 3 to 3, is there an interval? Absolutely not. Therefore, there is no area. That integral is 0. All right, let's move on. Do a couple more of these, a of 9 and f of 9. So if I do a of 9, I'm going to plug 9 in for that x. So I'm going to go, what is the area of this function from negative 1 to 9 of f of t dt? Now, from negative 1 to 9, which is over here, I need to take into account all 3 of these regions. So this one being negative, this one is positive, and that one's negative. What I can constitute that as is negative 27 plus the positive region and minus the negative region again. Therefore, this area, which again is a net area of negative 59. That should make sense that it's negative because more of the area is below the x-axis. All right, and then finally f of 9. Again, I'm going to put 9 right in here for x. So I'm going to go from 3 to 9 of f of t dt. So that means that I have to start here and go to here. So I need to account for this area and that area. So that would be 3 plus a negative 35 or minus 35. Therefore, this area, again, a net area is negative 32. All right, very good. So that's the area formula. We're going to continue with this to kind of get us somewhat of a proof, or maybe I can convince you with an example of our fundamental theorem of calculus part 1. All right, so here we are, have a function 2t plus 3, and we want to know, consider the trapezoid that's bounded by that linear function in the t-axis from t equaling 2, to t equaling x. The area function is given here, just like what was defined above. Gives the area of the trapezoid for x greater than or equal to 2. All right, so I'm going to graph that. Here's my t-axis. Here is x equaling 2. Here is, let's say, x, because that's what I'm looking for t equaling 2 to x. Now, that linear function means that I start on my y-axis at 3. I'm going to go up 2 and over 1, up 2 and over 1. So I'm just going to sketch that it's a linear. Again, we don't have to be so accurate with our graphs all the time. Now, what is the trapezoid that we're talking about? Well, it's the one that's bounded here with t equaling 2. And so up to that function, t equaling 2. And then if I just call that x, the trapezoid that we're looking at is this guy right here. So what I'm looking for is this area of that trapezoid using this integral. Now, let's talk about what a of 2 is and a of 5 before we go down here and kind of create an actual function in terms of that. So when I put 2 in for x, that means I need the integral from 2 to 2 of f of t dt. Well, we just kind of did one of those. Notice your upper and lower limits are the same. There is no area when x equals 2. You're right here. There's no area if we go from 2 to 2. But if I go from 2 to 5 of my function, and actually I'm going to go ahead and write that function in, which is 2t plus 3, so you get to see that. Then, since it's the area of a shape that I know geometrically how to find the area of, all through here, I can use that formula to help me out. So, that means for a trapezoid, don't forget the area of a trap is 1/2 height times base 1 plus base 2. That's what I want to find. So I'm going to do 1/2. Remember, the height is the distance from parallel side to parallel side. So that is this distance. Now, for the time being, this value is 5 because I'm going from 2 to 5. So to find a distance from 2 to 5, I use a subtraction of that. So do the kind of the b minus a type idea, take the larger minus the smaller. And then I need the length of this is base 1 and the length of this is base 2. Well, remember, this is f of t here. That's my function, 2t plus 3. So if I find f of 2, I'm going to add that to f of 5 to determine those base 1s and base 1 or base 2 lengths. So, simplifying now, we get a 3 here. Now, what is f of 2? Plug 2 in. I get 2 times 2 is 4 plus 3 is 7. And plug 5 in. 2 times 5 is 10 plus 3 is a 13. Well, if I multiply this out, those don't cancel very nicely, but this is 20. So if I do half of 20, that's 10 times 3 gives me 30. So the area from 2 to 5 of this function is going to be 30. But what if I wanted to generalize that? Can we determine just an area function in terms of x without the integral and figure out what that area function is? Well, if you recall, that will end up kind of modeling, just like when we had the velocity. If I went from the velocity function and I integrated, found the area underneath, we were looking at the position of that function. Here, we have a function, and when we integrate, we're finding the area of that. Okay, so I'm going to kind of take this idea that I just did a specific situation on and generalize it, because instead of having a 5 here, I'm going to have an x. So, a of x here is equal to the integral from 2 to x of that 2t plus 3 dt. So that's what we're trying to find. But again, we're not going to get an exact answer this time because I don't have a number up here in my upper limit. So I'm going to kind of take this idea here. And wherever I see the 5 that I placed in there, now if I replace that with an x, that means that this should change to an x and that should change to an x. So if I want to kind of go back to this here and change that back to an x, maybe we can see kind of how that we do that in terms of x. All right, so for our area of our trapezoid, we need 1/2 of our height, which is the difference of these two values. Now, before it was a 5, now it's an x, so I need to take x minus 2. Then I need to find base 1, which is going to exist at f of 2 still. But base 2 this time is at x. So it's now not at a number, so I need to plug in x into my function. And now, when I simplify all of this, I'm going to get one formula for the area of this trapezoid, okay, in terms of x. So I'm going to first find f of 2 and plug in f of x. So 1/2, I can't simplify anything here. F of 2 times 2 plus 3 gave me a 7. Plus, now if I plug x in there, the best I can write that is 2x plus 3 from that function. Now, I do want to simplify this a little bit. So I rewrite the first two. So I'm going to have a 2x plus a 10. Well, that's awfully nice that each one of those are divisible by 2 because I have this half hanging out here. Now, you don't want to do a half through here and a half through this one. You can do half of one or the other, but not both. So I'm going to think about distributing that 1/2 through this binomial. And when I do that, I'm going to keep the x minus 2, but when I distribute that, I'm going to divide both of those by 2, resulting in an x plus 5. Now, this is just algebra. We can FOIL this and get x squared in my first term. Outside is plus 5, inside's a plus 2 or a minus 2, so I get a plus 3x, and the last term is a minus 10. So what I have created here is an area function, a of x, in terms of x, that for any x value that I choose, I don't have to go back and do this. Basically what I've proven is that I could plug in x. So if I say, what's the area from 2 to 10, I would just plug in 10 and 10 and figure out what that is. So I've made a model of the area for this situation. So if I were to graph this function, now notice here, remember these factors are going to help me out with my zeros of this function. So that would mean what makes this 0 is -5, what makes that 0 is a 2. So if I were just to kind of sketch that, I'm going to have a 0 here, and I'm going to have a 0 here, but I want, remember this was defined to be greater than or equal to 2. So I'm going to have this parabola that does something like this, but the real function that I have in this situation is going to be modeled by just this piece where we are greater than or equal to 2. So that, again, can model for any x value what is the area of that particular trapezoid. Now, I said we were doing this kind of as an example to preclude part of this fundamental theorem of calculus that we're going to learn. What happens if I take the derivative of a? What does that look like compared to f? Well, first, I'm going to take the derivative of this function. Okay, so just like with our shortcuts, do the power rule. This would be a 2x and then a plus 3. So what I have here is the derivative of the function I just found, but what is f? Well, I've covered it up. F was the function 2t plus 3. So f of t is 2t plus 3, and if I talk about the dummy variables, does it really care whether I have x's or t's? This is the same as this, right? So what I've just kind of proven in this example is if I integrate or integrate to get a function, and then I take the derivative of that function, I basically get back what I started with. That in mathematics is what we call inverses. So basically this is proving that taking the derivative of an integral basically cancels itself out. It is an inverse of it. So now we move into our one of our parts I would say it's not the most important part of the fundamental theorem of calculus, but that's in my view. The second part's going to be so much more important. But this is kind of the foundation again, and making sure you are reminded that a derivative of an integral basically cancels itself out, just like multiplication undoes division, just like square rooting undoes squaring. Integrating undoes derivatives, or derivatives undo integration. Okay, so they are inverses. So for our fundamental theorem of calculus part 1, we are going to say that if we are given the area function a of x is equal to the integral from a to x of f of t dt, that's what we just defined on the backside, it is known that, and we just proved it in that example, if I take the derivative of that function, then we are taking the derivative of that integral a to x of f of t dt, which means that the area function of f is an antiderivative of f on AB. So, what I will say here, and in addition to this, is that a prime of x will equal f of x. Now, there's a kind of a precursor to that if this value up here is something other than x, when you have this x squared or 5x squared or whatever the case may be, then you have to chain rule that. Okay? So, if you have one function, then you have that, but if you have two functions like what we're going to deal with right here, I'm going to kind of do this piece where you have to do kind of the composition of the two functions and then take the derivative of that extra piece. Okay, so it's pretty simple. It's just kind of making sure you recognize what they're asking, and then to actually find the answer is not very hard. So if we're trying to find the derivative of the integral, realizing that this basically cancels that out, what I'm doing basically is taking that x value and plugging it in for t. So this is what we're kind of looking at here. This is like examples 1 and 2 below. This one is going to be for our third example here. Okay? So if I take x and I plug it in there, basically what I get is the sine squared of x, and that's my answer. Again, it cancels out the operations, leaving us with just the function in terms of x. Now this time, I don't have just a number down here and my variable up here. They're switched. But there is a property of integrals that I can switch my lower and upper bound. So in order to do that, I hope you recall that you have to take a negative out. And so then we get the negative of the derivative from now 5 to x of the square root of t squared plus 1 dt. So again, here's a derivative that's going to cancel out this integration. I need to take this x and plug it into my f function, and my answer is going to be where I have x squared plus 1 under that square root for this piece, but I can't forget about that negative. So my final answer will be this. And then our final one is dealing with this piece here. Again, if you have something other than x, you have got to chain rule and take the derivative of that top piece as well. Okay, there's a proof in your book if you want to go look at it in this section. So these kind of cancel themselves out. I'm going to plug this into the variable and then chain rule. Okay, chain rule the upper limit is what I'm going to say. Okay, so if I put x squared in for t, now notice that that is squared also. So I get the cosine of x squared squared. And then I have to chain rule that upper limit. So the derivative of that piece is 2x. So cleaning that all up into just something that's simple. Normally we bring this in front of a trig function. So I get 2x cosine of x squared to the squared is x to the fourth. And that would be our final answer. Again, foundation here of making sure you realize that taking the derivative of an integral is an inverse, and it just kind of cancels itself out, okay? But here is what we've spent the last couple sections building up to, okay? We've found through Riemann sums that we are approximating areas to the area under a curve. Then we expanded that to what if I went from n equaling 4 subintervals to 10 subintervals to 75 subintervals, all the way to infinity subintervals. And at the end of chapter or section 2, we did that Riemann sum to find the exact area. But it was a really long problem, and it took us a whole page to get it done. Obviously, that is not the most efficient way to find a definite integral. So here is the way that we are going to be efficient in finding definite integrals, and it's called the fundamental theorem of calculus. In your book, they call it part 2, but this is what a lot of people were referred to as the fundamental theorem of calculus versus what we were just kind of doing. I mean, it's still the same thing, comes from the fundamental, but here is usually what people are referring to. So we have a function that is continuous on a closed interval AB, and I'm going to say that capital F is the antiderivative of this function on the closed interval of AB. Then the integral from A to B of f of x dx, which by meaning is finding the area under that curve from A to B, that is equal to capital F of B minus capital F of A. So remember, capital F is an antiderivative of F. So that's why section 4.9 is going to be so important here, because we have to go backwards to find that integral. But now, to find the exact number, the exact area, I have to evaluate at B and evaluate at A. And then you're going to get a number. And that number is going to represent the area under that curve. So, reminding you of some notation, or actually how that we kind of get this. Remember, from A to B, these are my limits, my upper limit, my lower limit of f of x dx. A lot of times, what will happen is that we will find the antiderivative, call it f of x, and we will evaluate it at A and B. Now, that is the way some books do it. I will tell you that I will do f of x, and I will put a bracket around those to represent evaluating at A and B. But that just means that we take f of b, we're putting our upper limit in first, and subtracting the evaluation of that at the lower limit of A. And that is huge. Huge, huge, huge to be able to do this. So here's our first 4 that we're going to look at. And then we'll do some difference between net area and actual area. All right, so I want to find the definite integral of 60x minus 6x squared dx from 0 to 10 using the fundamental theorem of calculus. So what this tells me is that I now need to figure out what is the antiderivative of this function. So remember how we go backwards of our power rule. We're going to add 1 to this power of 1 to give us an x squared and divide by 2. That I want to multiply by that 60. Now, hopefully you're kind of getting used to some of this where you're doing it in your head a little bit more. I'm going to add 1 to get an x cubed. I can divide by 3, but I can mentally divide by 3 as well to give me a 2. So here is what I want to evaluate at 0 and 10. Now, of course, I'm going to simplify in here as much as I can. So this is actually going to be 30x squared minus 2x cubed that I want to evaluate at 0 and 10. Okay, so here we go. I need to plug 10 in. This is my f of b. I'm going to plug 10 in. And when I do that, I get 30 times 10 squared minus 2 times 10 cubed. That is just my f of b. That's evaluating when x equals 10. Minus, now I need to put my lower limit in. So 0 in here and 0 in here gives me 30 times 0 squared minus 2 times 0 cubed. Well, you will find out that having 0 as a lower limit or even an upper limit is going to be so helpful, especially when you have polynomials. Not so much always when you have trig, you better watch that out, but when you have polynomials, that's all gone. That is 0. And all you have to figure out is what this is here. Okay, so 3 times 100 gives me, or 30 times 100 is 3,000. 2 times 1,000 is 2,000. When I subtract those, the area under that curve. Now remember, this is a net area under that curve for this function is 1,000. Okay? All right, let's try this guy. This one has a couple things going for us that we can kind of look at. First off, I don't know how to integrate that without it being a power. So I need to change that from 4 to 16 of 3x to the 1/2 power dx. Now, you are more than welcome to go ahead and integrate this like you have in section 4 or 9, but we also in section 4 or 9 were taught that we could also pull that number out front. So if you so choose to integrate just 4 to 16 of x to the 1/2 dx, you are more than perfect to be able to do that. So either way works. So I'm going to go ahead and integrate that. So I'm going to keep my 3. When I integrate 1/2, remember when I add 1 to that, when I add 1, that's the same as 2 over 2. So when I add 1, that gives me a 3 over 2. Now, I don't want to divide by 3/2. When you have a fraction, remember instead of dividing by the fraction of the power, multiply by the reciprocal of that and bring that 2/3 out front. That's what I would do, okay? And then I'm going to put my lower and upper limits here for that. Now, you can put 16 in and 4 in and keep the 2/3 here, but you could also combine these because these are all multiplied together. So you can bring this out front as well. So if I do 3 times 2/3, I just get a 2. And now I can just get it down to as simple as I can get it, where I now just have to evaluate 16 in for x and 4 in for x. So when I do that, I'm going to come back over here. I get 2. Let's go 16 to the 3/2 minus 4 to the 3/2. And this comes in our fractional exponents. Remember, this is the square root of 16 cubed, or cube 16 then square root. I would do the square root first. So the square root of 16 is 4. 4 cubed is 64. Minus the square root of 4 is 2. 2 cubed is 8. So I have 64 minus 8, which is a 56. And doubling of 56 is 112. So if you go back to one of the problems, I believe it was in section 5.1, possibly when we did a left and a right and a midpoint Riemann sum, we had this function from 4 to 16. We had that exact same example. And I told you at that point 112 was the area. And here we've just proven it by the fundamental theorem of calculus, which is beautiful. This is a great, great tool to know, okay? All right, let's do a trig one. First, I'm looking at this trig function. I'm going to, again, choose to bring the 3 out front and integrate from 0 to 2 pi of sine of x dx. Now, you have to remind yourselves of what those trig integrals are. So if you need to go back to section 4.9 and look at those, please do so. Now, what function did we take the derivative of to get sine? Well, it had to be cosine, but when I take the derivative of cosine, it's negative sine. So therefore, the integral of sine is going to give me a negative cosine answer. So I need negative cosine of x that I want to evaluate at 0 and 2 pi. Now, again, you can put 2 pi in here, you can put 0 in there and keep that negative, but I'm also kind of showing you some things too to help you out. Go ahead and pull that negative out so you don't make a mistake. And then plug in the 2 pi. So I get cosine of 2 pi minus cosine of 0, and then I don't have to worry about that negative. Now, here's where knowing your trig functions is important. Cosine of 2 pi, that's all the way around the unit circle one time, that's a 1, which is the same angle at 0. So its value is also 1. Therefore, this becomes 0 times negative 3 would still be 0 as well. So again, the net area of that is 0. Well, does that make sense? 3 sine of x goes up 3 and down 3. You go up like this and down for one period. So it should make sense that that's 0 because that area is positive, that area is negative, and they are the same. So they're going to cancel themselves out for the net area to get a value of 0. All right, very good. I'm hoping things are kind of meshing together and you're kind of getting some aha moments here. So I'm going to go ahead and modify this function on this last example here. And in order to integrate that with a power, I need to, don't forget, distribute that power of t to the first power to both of those terms in the top. Now this is t to the 1/2. And when I have t to the 1/2 over t to the first, we can subtract those exponents. So if I do 1/2 minus 1, then this integral from 1/16 to 1/4 is going to be t to the minus 1/2, and these t's are going to cancel, so minus 2. And that's what I need to integrate. So I like to give you a couple of these fraction ones so you see that when I take the antiderivative of that, remember, take plus 1 of your power, so negative 1/2 plus 2/2. is going to be t to the 1/2. That's a fraction. Don't divide by 1/2. Multiply by the reciprocal of that and get the 2 out front. Minus, now when I integrate just a constant, remember that had to be a linear term, that when I took the derivative, I just got a -2. So that's going to be my last term, and I need to evaluate that at 1/16 and 1/4. Now here's just a lot of algebra. Now, you have the right, if you want, to go ahead and plug in 1/4 and plug in 1/16 and do the subtraction between the two. I like to kind of clean some stuff up. So I'm first going to factor out a 2 and be left with t to the 1/2 minus t that I need to evaluate at 1/4 and 1/16. So remember, the upper limit goes first. So I'm going to come back over here, and I'm going to do 1/4 to the 1/2 minus 1/4. And that right there is just my f of b. That's just plugging that in. But I now have to subtract f of a. So I need to plug 1/16 in here and 1/16 in here. So I have 1/16 to the 1/2 minus 1/16. Now be very careful. There's a minus between there. So if you're going to kind of run through and simplify without kind of doing this first, and you may want to distribute, don't forget to distribute that negative, which is what I'm going to do, okay? So I have the 2 out front. Half of a number, with that as a power, that's just the square root of that number. So the square root of 1/4 is 1/2. Square root at the top and square root at the bottom. Minus this 1/4 minus this, so the square root of 1/16, square root at the top, square root at the bottom, I get a 1/4 again. But be careful, a minus and a minus here, make sure you do a plus 1/16. Now, here's where you want to get a common denominator, which would be 16th, and when you add 1/2 minus 1/4 minus 1/4 plus 1/16, if you need to have a calculator help you with that, then by all means do so. Twice of 1/16, if I multiply those together, gives me a final answer of 1/8. So, it can be a little bit tedious on some algebra, but you always have to make sure you're meticulous in all places. All right, very good. Let's continue to our last little example in this section. So, the key thing that I really want you to practice in section 5.3 is that fundamental theorem of calculus, where you're taking the antiderivative of that, plugging in b, plugging in a, and subtracting those two. That is crucial that you are able to do that. Now, when doing an integral like the ones above, you are technically finding the net area. Remember, we talked about that with the sine curve. So, if the function is positive in some places and negative in some places, then you will be summing together positive and negative values. If the area of the region is requested and part of the area is below the axis, then that needs to be accounted for by breaking up regions and accounting to get the positive area of a negative region. Hence, we have this example. So, the graph of f of x is equal to 6x, x plus 1 times x minus 2 is given to us. The region R1 is bounded by the curve in the x-axis on the interval from -1 to 0. And region 2 is bounded on the curve in the x-axis from 0 to 2. Now, notice, if I ask for the net area, then we're really just looking at from -1 to 2 of our function f of x, okay? Now, let me do a little bit of work on f of x. Here, we don't like to integrate anything like that. If I could get it into a polynomial, that would be very nice. So I'm going to FOIL here, do a little x squared, then a minus 2 plus 1 is a minus x, and then my last term is a minus 2. Then I'm going to distribute the 6x to get a 6x cubed minus 6x squared minus 12x. And that's what I want to put in my integral. That's my function. So to find the net area, there's really nothing you have to really think about except for figuring out what the integral is. So I need 6x cubed minus 6x squared minus 12x. We're going to integrate that with respect to x. So when I do that, let's take the integral of this. Let's add 1 to our power so we get an x to the 4th. But then I have to divide by 4. Well, if I have 6 over 4, that's not very nice. I can reduce it, though, to become 3/2. So hopefully you're getting to the point when you're taking antiderivative, you can do them in your head. If you need to write them all out again, please do so. All right, so I'm going to add 1 to this power, which is a 3. When I divide by 3 up here, that leaves me a 2. When I add 1 to this power, I get an x squared, but when I divide by 2, I get a 6. So here is what we want to do. Now, before, if I didn't have any upper or lower limits, remember we did our plus c as our arbitrary constant, and we were done. But with the fundamental theorem of calculus, we don't care about that arbitrary constant. We now need to evaluate at -1 and 2. So here we go with that. If I put 2 in here, 2 to the 4th power is 16. Divide by 2 is 8, times 3 is 24. So I get 24 for my first term. Again, I'm going to plug 2 in here. 2 cubed is 8, times 2 is 16. Minus, here I get 2 squared, which is 4, times 6 is 24. So that is just my f of 2. Minus, now I get to plug in -1. Well, -1 to the 4th power is a 1. Times 3 halves is 3 halves. -1 in here makes this -1 times -2 is a plus 2. Oops. Plus 2. And then -1 in here squared is 1 times a -6 is a -6. So this is what we now need to figure out in order to find out what our net area is. So these are going to cancel, obviously. Throw the rest in a calculator, figure out what this number is. I don't care how you combine that. But your answer that you should get is -27 halves. So if you have to pause the screencast to be able to check your work, please do so. All right, now does that make sense? Is the net area, should it be negative? Well, look at the comparison between R1 and R2. The bigger region is down here, so it should make sense that that is negative. Now, what the problem is here on the next question is that it wants to find the area of the region between the curves and the x-axis. And the problem here is that part of the region is above and part of the region is below. And so here's the case where I have to kind of account for both regions separately. So I want to take region 1 and add it to region 2, but in this case I have to have the absolute value of region 2. So really, region 1 plus the absolute value of region 2 is going to equal the area that I'm looking for. Okay, so let's just find the area of region 1. That is going from -1 to 0 of the function 6x cubed minus 6x squared minus 12x dx. Now, the big thing is we've already integrated this. We already know what it is. Right here is the antiderivative, but I'm going to change my integrands here. So this is equal to 3 halves x to the 4th minus 2x cubed minus 6x squared. Now, instead of evaluating at 2 and -1, I'm evaluating at 0 and -1. Now, what did I tell you about 0 in polynomials? 0 is very nice because when I plug 0 in and 0 in and 0 in, all of those are 0. So the first thing there is 0. And I want to subtract now f of -1, okay? So I need to plug -1 in. Well, we just did that right here. So that is 3 halves plus 2 minus 6. All right, so we have an advantage because we already did the net area. Most of the time, you're not going to do both, but here we have that. All right, so if I do 3 halves plus 2 minus 6, then that gives me an area of 5 halves. So if you try that and don't get 5 halves, something's wrong. Try again. Okay, now region 2, though, goes from 0 to 2. So I need to integrate from 0 to 2 of our 6x cubed minus 6x squared minus 12x dx. Okay, and again, we have the advantage because we already did the antiderivative. So that is 3 halves x to the 4th minus 2x cubed minus 6x squared. And from from 0 to 2. Now, again, we have a 0. That's awfully nice because that's where the region's kind of separated there. I'm going to plug 2 in, and the advantage is I already plugged 2 in earlier. Again, we have the advantage because we did the net area. Most of the time, you're not going to have that, so you would have to do this work. So here I get 24 minus 16 minus 24, and then when I plug 0 into all those, I'm subtracting the 0. So these are going to cancel, leaving me with an area of -16. But remember, we don't want that -16. That is the area. The negative tells me it's below the x-axis. But if I want the area of the total region, again, it's like I got to bring this up here. That's not very symmetric, but find the area of it up here and then add those together. Okay, so that's what we're symbolizing when we're taking the absolute value of that region 2. So the area total comes from taking region 1 plus the absolute value of region 2, which is 5/2, plus the absolute value of -16, getting a common denominator, and adding those together leaves you with an area of 37/2. So you just can't assume that you are just taking the opposite of this, because remember, this was a positive minus a negative. There was a net area there. So this should be higher than the absolute value of that net area. Okay? So another way that I could evaluate this or show that I wanted the area of the region one last time is if I go from -1 to 2 of the absolute value of f of x dx. And that would symbolize the total area of the function versus the net area in that. Okay? All right, very good. So that is a huge section for you to make sure that you know how to do those fundamental theorem of calculus, finding your f of b minus your f of a after you take an antiderivative. Our next section is going to be dealing with some techniques to help us out when integrating. How can we evaluate a function a little bit easier when we know some things about that function. And we're also going to be talking about average value of the function and the mean value theorem for integrals, okay? So until next time.